start my timer. So this talk is another talk that's a little bit kind of a new thing that's happening. So we're not going to have data at the end, unfortunately, which is, I always like the talks with the data at the end. But this is inspired by the kind of analysis that I just showed you. And next Soar workshop, we will be able to show you data because this is actually, funded work that we're pursuing. So not many talks this year about ITL. You'll hear the last half of this afternoon. We'll kind of deal with. We'll talk a little bit about ITL in the context of a big project that we're doing. But for a long time now, 15 plus years, several PhD theses in the room, people have been thinking about how do we build systems that can learn from learning a task through instruction, right? And so we'd like to be able to have agents that learn tasks from instructions. And what I'm going to be pursuing and talking about in this talk is, what if we just use LLMs, or specifically agentic LLM systems, to do that task learning? So this will be a little bit in contrast to the ITL stuff that you might have seen in the past. And the notion is that we'd like to be able to use LLMs because they kind of have two obvious benefits, and maybe there's a third one. One is that they could increase the generality of our systems because they just have all this prior world knowledge that they can bring to bear. They might decrease the cost of training and instruction, one, because they can just operationalize the interaction between the human and the system a lot better. And another one is that they might be able to actually exploit a lot of existing natural language artifacts, documentation, so that the human doesn't have to explain all that, right? So if I can just kind of read a 400-page manual before I sit down and come to the class, then I'm in a much better position, should be in a much better position to learn than if I haven't looked at that. But language models also have this problem, especially hallucinations, but also if they've got stuff in them, if their priors include things that are similar to the things I want you to learn, but they're actually different than what I want you to learn, that can kind of become an interference for learning as well. So the question is, well, I guess before I go there, just like these things really prevent scaling. So if we can't overcome these limitations, then it's not completely clear that language models are that good for these problems. So this is the slide I was alluding to, that a lot of the work that we've been, so first of all, just on the left-hand side, you could just throw generative AI at this and say, we're going to solve that problem. And there are people out there that are doing that, and bless them. That is not really what CIC is going to do. In the main, what CIC is doing is thinking about a sort of source-centric approach, or maybe I'll just say cognition-centric approach. We've talked about a bunch of different things over the past few years, and including things that you'll see more of this afternoon with Soar, where we're going to leverage the pink stuff in this figure is all language models, by the way. I left that out. Where we definitely want to leverage language models, but we're mainly leveraging them as content. So the architecture is the architecture that we are familiar with, and we're using language models in different ways and for different purposes, but basically at the level of becoming content. And what I'm going to do in this talk is not a very Soar specific talk in a way, is to say, well, we're just going to think about what if we just took a purely agentic LLM approach, where the architecture, we're going to create an architecture that's inspired by a lot of these boxes in Soar, but they're going to be implemented with LLM nodes, not with Soar. And so it's a little bit of a thought exercise for this talk. So here is a situation that, just to ground this kind of concept of what I want to talk about, very concrete thing. So I want ChatGPT or some system to play cards with me. And if it doesn't already know how to play cards, I should be able to just give it Hoyles. And it says, okay, I got Hoyles. I know all the rules and Hoyles. But I should also be able to say, in my house, when we play rummy, you have to pick up the whole deck when you pick up cards. You can't just flip through the cards, or whichever way Hoyle says my family plays.
That's the other one.
Yeah. And the humans there also to give feedback, right? So we can't really expect this ungrounded language model to be able to learn everything from first experience. So, we still want the human to provide some feedback. And then maybe what the system learns is it learns I know how to play gin rummy. I know how to play hearts. I know how to play euchre. And so we've got a system that's kind of incorporate that in some kind of long-term memory. So the context for the way we're thinking about this problem is I just talked to you about cognitive design patterns. And what we want to really do here is think about, well, if we can apply this notion of cognitive design patterns to this learning from instruction with language models problem, our notion is that the cognitive design pattern should give us kind of more fine-grained, more kind of controlled thought generation, to use the React term, thought generation. And then that should lead to more reliable reasoning. So that's a testable hypothesis that, sort of it's a meta hypothesis here because we're really focused on this task learning, but that's part of the idea, is to operationalize some of these ideas about cognitive design patterns as well. So the next part of this talk is I'm just going to tell you about what we're doing. So we've chosen 2 cognitive design patterns to focus on, hierarchical task decomposition and compilation. We talked a little bit about compilation this morning, so I was like chomping at the bit to jump in, and really we chose this 2 because they're very synergistic and obviously very relevant to task learning. So one is, if I am learning how to do a task, I want to break that into smaller tasks. It's just easier to understand and learn that way. But then I don't want to have to do all those individual thinking through all those steps every single time, right? And so that's where the compilation comes in. This is like a Soar 101 story. This is the kind of stuff, if we were having a tutorial this year, by the end of the first day of the tutorial, this is something that you would be doing in Soar, right? So what we want to do is see, can we get a agentic LLM system to do this, something like this? And we have these different hypotheses. I'm not going to go through the details of the hypotheses here, but I'm just going to kind of talk you through what the vision is, and you'll get a sense of where we're going. So now, instead of learning how to play hearts, you're learning a bunch of different things about playing cards. And some of those things that you learn about playing cards are applicable to gin rummy, and some of the things you learn about playing cards are applicable to spades, like making bids, for example, that's true for euchre and hearts and spades, I think, but it's not true for rummy. You don't do bids for rummy. So those are kind of what some of those things mean. And now we're going to need a different kind of feedback from the person, because now we need them to say something about how these different subtasks relate to different games and to the different decompositions. So they might be providing feedback about the agent's decomposition, and they might be providing feedback about how some decomposed part of some task applies to a task. And then here's the kind of thing that we would hope to see. So this is, a completely speculative chart, but the horizontal axis here is within a domain, the number of new tasks that you see in a domain. And the vertical axis here is some normalized notion of effort that includes human effort, that feedback that the human is providing, but also computational effort, mainly in terms of token use and token generation. And so if we looked at the ideal case, what we'd like to see is something like, I learn a little bit about the domain and immediately start leveraging that for lots of new tasks, and I just learn really fast. And maybe you would approach something like a power law. There was a huge amount of transfer between all these tasks in the domain that I would just learn super fast. So that's the ideal. Our expectation today for large reasoning models is, even though they might be able to learn these tasks without a whole lot of training, whenever they do a new task, unless there's some managing of context windows or something, so we start getting into more agentic LLM architectures, they're not going to see a lot of amortization of reasoning about euchre carrying over to reasoning about spades, right? And so they're going to have to do it over and over again. And our expectation for what we're working on is, if we're successful, is that, early on there might not be a lot of benefit, because there's a lot of different tasks, and maybe that's kind of figure out how to tune the task. But after some period of time, we should start seeing some benefit as we introduce more tasks in the domain. So that's kind of what we're going for. So let's talk a little bit about these 2 cognitive design patterns. So hierarchical task decomposition is the first one that I want to mention. And as I said earlier, just breaking down the task into simpler goals and tasks. So it has this recursive aspect to it. And a key feature, certainly feature in Soar, it's a feature in all these other plan execution agents that do this hierarchical task decomposition, is that it has an adaptive nature to this decomposition. It's not like saying, here's the way the world gets decomposed, and then I'm just following that path. But you're making decisions as you're seeing the world unfold about how you're decomposing it. Oftentimes, maybe within a narrow frame, but you're still doing that dynamic decomposition. So there's lots of work out there, a huge amount of work, much more than I thought when I first got started, about lots of people who are doing dynamic, doing kinds of task decomposition with language models. These are a few. I think one of those is from Europe's and one from AAAI. Couple of features about these is that they generally have very shallow decompositions. 3 levels is about as deep as they go. And most of the time, it's like a planning process where they're deciding the details of the decomposition and then they do it. They're not making this dynamic decision about how to decompose the task as they go. All right. So, and I'm running out of time here, so I'm just gonna say that there's clearly an opportunity here to kind of think about Soar operator subgoaling, kinds of patterns, and then do that kind of thing in language models. So knowledge compilation, as I mentioned, we touched on knowledge compilation this morning. That's that chunking, caching of results from reasoning. This is a pattern that occurs again and again. It turns out that lots of language models do something that looks like knowledge compilation, although almost all of them that do knowledge compilation do it in a program synthesis kind of way. So they move away from language and look at it as a program. So the classic example of this is Voyager, the system that learned Minecraft crafting recipes, right? And what it learned was the JavaScript for the recipe, and it had a clever mechanism for retrieving that when it needed to compose it with other ones. There is a system called Expel, which was published at AAAI last year, and it is not doing that program synthesis thing. It is like, I'm going to try out a bunch of experiences, I'm going to learn from those experiences, and then I'm going to derive these insights from these experiences. These insights, this is taken from the appendix of their paper, they look a lot like what we would think of as search control in Soar. There are rules in Soar that you're going to see later that are very similar to the rules that they're using in a system called AlfWorld, which is a text-based robotic world. So this is where we're going in terms of an architecture. I won't have time to go through this today, but you can ask questions about it. But some of the key things that we have here are a question about whether or not we actually need a stack of memories. So you need a memory associated with each of the decomposition, which is kind of what Soar does with the MPass memory. And then there's this question about, as I mentioned in the previous talk, about do we need mini reflect in something like reflect? So sorry I ran out of time, but I think I'm looking forward to this project because it's a way to put some of these ideas into practice, but it's early, so we don't have a lot of results yet. I think this is a key thing that's missing in intelligent systems, this notion of instruction and teachability. But we also see that there's a lot of dependence on the domains that you choose in terms of the outcomes that you get. And then high payoff, guess what the goal is? High risk. So there's a lot of benefit here for this problem formulation going after this, but it's pretty open-ended how successful we'll be. All right, so I still have 1 minute for questions.
I have a question. I find like this dynamic decomposing idea is quite fascinating. My question is like, where the decomposing happen every time when the environment changes, or the decomposing will be iterative, adapt to the first iteration of the decomposed tasks.
Yeah, so that's an insightful question because what we would do is to say that you need to think about the decomposition each time that you face the task, and then if it's a similar situation and you know the decomposition that you've used in the past is apt, you don't go through all the
Yeah.
You just get them
sorry, that might be background noise, but yeah, so that is one of the things that we'd like to do is have a mixture of both, but where you're making a deliberate decision about when to decompose.
I see.
Cuando encuentras gente de alfa